Right, so here's the problem where some of you guys are going to stuck. How do you convert from millimeters of mercury to atmospheres? Okay, so you're taking 697.68 millimeters of mercury, and you've recognized the relationship. Well, I'm showing the conversion, right? So I know the relationship between millimeters of mercury and atmospheres. What is it? 760 what? Millimeters of mercury, and I'm going to put that top or bottom? Bottom, because I want to cancel millimeters of mercury, and that's converted to 1 atmosphere. So if you don't understand this process here, you gotta let me know later, because this is just an idea of like 1 foot is equal to 12 inches, 1 atmosphere is equal to 760 mils of mercury. That's just what the conversion is. All right, so this millimeters of mercury cancels. What is 697 blah 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 divided by 760? 0.918 atmospheres. All right, great. So now we have a real pressure that we can plug in and cancel units with. Okay, so what else needs to be converted correctly to correct units? I mean, so this, how do I get from Celsius to Kelvin? 273. Okay, great. So what is this? 283 Kelvin. All right. So now this is a little messy, but we have all of our units correct. So after we wrote down our givens and we recognized our gas laws as the ideal gas law, and we're like, oh gosh, we got R. R doesn't agree with any of these units. We've now corrected our units. Now what do I do? So how do I set this formula up if I'm looking for N? Divide by R and T on both sides, correct? Because I have to do that to both sides to make both sides of the equation equivalent. So what happens to the right side? They cancel. So N is equal to PV divided by RT. And I like to rewrite it just because I can easily make sure I'm not plugging something in incorrectly if I do that. So this is what I really have narrowed down when I'm solving for N. What's P? 0.918 what? ATMs, atmospheres, right? You have to put your units there. If not, it doesn't help to make sure that you're kind of double checking yourself to make sure everything's canceling. What's volume? Liters. Okay, so 0.1000 liters. Okay, so that's P and V over, what's R? 0.0821 atmospheres times liters over moles times Kelvin. Woo, that's a rough unit, but do write the entire thing out, and I'll make sure you can see how they cancel as well. And then what's T? 283 Kelvin. Perfect. Okay, so here's the problem. I see this mole way down here in the bottom, right? But it's in the denominator of the denominator. So whenever you divide and you cancel all the units out, you see atmospheres in the numerator of the numerator and in the numerator of the denominator. So they cancel because one's on top, one's on bottom still. Same thing with liters. Numerator and then numerator of the denominator, but still there's one there on top of each other, so they can cancel. Now this Kelvin, I have it drawn on the same plane, but is it really? No, this is in the numerator of the denominator, and this is in the denominator of the denominator, right? Basically, there's still one on top, one on bottom. So Kelvin can cancel. So the only unit remaining is mole, which is what we wanted. Great. Now with this though, when you do your floppy dot chop, whatever that is you guys do, it moves to the top. But I always like multiply the numerator and then denominator and then the middle two and then the units. This unit flips back up to the top. So regardless, it's still going to be solving for moles. So let's go ahead and divide this and let's see what you guys get. Make sure you're putting parentheses where they belong.
So regardless of the number, the moles will still be there.
The moles will be there.
Like, no matter what the number is that we multiply by, like the moles.
Because the moles are in the denominator, they move to the top when you divide. Because it I don't know how to math. This is why math's a prereq, because it's like x over y and a over b. So when you multiply by b over a, and that cancels, well, b, which is moles, moves to the top. It's like multiplying by the reciprocal. Yeah. Oh, we're gonna make its own number by dividing. We're gonna calculate the number that moles correlates with. No, we're gonna put the unit of mole on the number we get here. Yeah. So 0.918 times 0.1 in parentheses divided by parentheses 0.0821 times 283. What'd you guys get? I hear 0. Point what? I'm a scientific notation person. 3.10 to the negative. Oh, hold up. I put an extra 0 in. Hold on. It is a 3. It's not a 4. Yes, negative third. And so this number we got correlates with what unit? Moles. Okay, woo. We have solved for moles. We have solved for N. Now, I know you've already forgotten the question. What the heck was the question?
Molar.
Solve for molar mass. So think to yourself, I've written out molar mass a million times. What are the units of molar mass?
Grams over mole.
Grams over moles. Do I have grams? Yes, I do. What is it? 2.62. Do I have moles? Yes, right here. How do I get grams over moles? Take the grams divided by these moles. Yep, that's how you're going to get grams per mole, which is what our issue of molar mass is. So, this is a big thick pen, but we're going. So 2.62 grams. Molar mass is grams per mole, which is 2.62 grams divided by 3.95 times 10 to the negative third moles. And what is that when you guys get there? 600. What is it? 663 grams per mole, which is just what the unit is because they don't cancel. And then I would round that. How many sig figs? This one right here has what? 3 sig figs. So this would be finalized to be what? 663 grams per mole. Okay. That was a rough one because at the end you had to do something you really had never done before, but it's not really all that new because you already knew what molar mass was, and so if you were looking at the data you had, and that's all you have to work with, you really had no choice. You had to take grams divided by moles to get to 663. Okay, so I'll maybe do 18 shortly. Ideal gas law, it's just about converting to appropriate units, plugging them in, and you should be canceling everything except the thing you're looking for. So in that case, let's go back to Dalton's law because we didn't get to finish this yet. So this is what you're writing in your foldable. Dalton's law is very simple. And we have a lab thing. So Dalton's law is called Dalton's law of partial pressures. So Dalton's law of partial pressures means that we take each individual pressure take it back to your seat, okay. We take each individual pressure of a mixture and we add them together. That's it. Now, is it easy for you guys to say, okay, I'm going to add, let's see the distance to, I don't know, to Chick-fil-A. Okay, so it's like 12 feet plus a mile plus 36 yards plus 18 inches. That's about how long it is. How long is that? Whatever. The units don't match up, right? So it's really difficult to add that together. What would be easier? If all those numbers were, of course, the same unit. So I could go, it's a quarter mile and then a half a mile and then another quarter mile. Well, how long is that? A quarter mile plus a half a mile plus another quarter mile. That's 1 mile, right? You just added those up as the units work. Well, we got to do the same thing here. When we're doing Dalton's law of partial pressures and we're adding up these, we're summating, right? Summation means to add. We're adding up those partial pressures together. They should be the same unit. If not, it just doesn't, it's not friendly and we have to do a lot of converting. So, let's talk about the atmosphere. Shout out some gases in our atmosphere. Nitrogen. How do I write nitrogen? N2. What else? Of course, there is oxygen, right? Okay, so there's like 70, oh gosh, 71? I might be wrong, but I think there's 71% nitrogen in the atmosphere, about 21% oxygen. I think that's off. It's like 78. Yeah, I thought it was higher. Okay. And then give me some more. I heard. What'd you say? Helium. I don't know the percentages. I'm just going to call it 1%. It's less than that, but it's close. What else? Carbon dioxide, right? That's a greenhouse gas. So it's 78. Oh, it's already 99. Is that right? Well, 0.1 and 0.9. Okay, so there's some other miscellaneous gases like argon, some water vapor, a series of gases. So let's say maybe there's like 8 different gases in the atmosphere. Well, if we're at our atmospheric pressure, what should they be equivalent to? 1 atmosphere, which is our baseline total pressure. So what we do with these, I could, of course, convert all of these to partial pressures and go, okay, well, nitrogen's actually, it's partial pressure. We always write P for pressure, and we label it with what we're identifying as, in this case, of nitrogen. Let's say it's like 0.78 atmospheres. And then pressure of oxygen is 0.21 atmospheres. And helium is 0.001 atmospheres. And partial pressure of carbon dioxide is 0.009 atmospheres. Well, partial pressures added together equal what? 1 atmosphere. So all of these add together to be P total, which we call PT, P total, the entire atmospheric pressure, which in our normal atmospheric conditions is 1 atmosphere. Now, when it's raining outside and we have a cold front or a warm front, the total pressure of our atmosphere changes slightly just because of weather. But this is our generic way of explaining it. So basically, make sure they're all in the same unit, take each of the pressures given to you, add them up, they must equal total pressure. Otherwise, I can ask it in a slightly different way and tell you information about the total pressure, and you solve for an internal pressure, one thing you may not know. So if you want to be adding this in your foldable, you're kind of killing 2 birds with 1 stone, because I asked for an example and like a scenario, right? Wink, wink. You got me? Are you adding this in your foldable? Okay, cool. You do you. All right. So a container contains. Container A contains a gas under 3.24 atmospheres of pressure. Container B is under 2.82. Container C is under 1.21. If all these gases were put into container D, what would the pressure be of container D? What do you think you should be doing here? Okay, writing down the given. So pressure A, 324 atm. Pressure B, container B, 2.82 atm. Pressure of container C is 1.21 atm. And it's what are we doing with these? Hold on, what are we doing with them in this scenario? Yeah, so who's ever gone scuba diving? Anybody? I'm so jealous. I've never been. I want to go. So, you get your little scuba diving self, your goggles, okay, and then you're smiling, and you get your little backpack on. Hey, what's up?
We're doing the promotion for the school, whatever. Is there like we just film your science class?
Sure, we're gonna do a lab in about 5. If you give me some
5
time.
minutes?
Give me 5.
Awesome.
Bye. Okay, so this is not a rocket. This is a scuba diving tank. Okay, bubble, bubble, bubble. What do they put in the scuba diving tank? Helium and nitrogen and little oxygen. There's nitrogen right there. That sounds good. Helium, oxygen. Helium is an inert gas, and I was hearing from all your endangered elements, so that's really nice. You guys remember that. So basically, this could be in a scenario of scuba diver guy with his like laser eyes. He's gonna go look for cool creatures under the sea. He's got 3 different gases in his scuba diving tank, and these are the 3 gases. Well, what if the pressure was super duper duper high? What would happen to the tank? It would probably explode, and the poor guy would never come back. If he did, he'd be messed up. Okay, so what's the total pressure of my tank? What do I do here? Add these up. What do you guys get? Say again? I was really hoping you guys had already added this up. 7.27. I believe you. Can I get a second on that?
Yep.
Awesome. Okay, so 7.27 atmospheres is what the pressure is inside the tank. That's really high. That's super duper high. But it's not going to be so high that the tank pops and then the guy doesn't come back. or the girl, you know. There we go. Okay, two pieces of hair. All right. So I try to keep it entertaining, guys. Okay, so basically you can see Dalton's law is quite easy. It's just the summation. I could have given you the total pressure and said, okay, what's the pressure of oxygen gas by asking for what PA was. And you would just subtract to solve for that. So the lab we're doing today is based on the ideal gas law and Dalton's law. It's going to utilize a couple of different scenarios. So I'm going to take about 5 minutes or so to explain the information regarding the lab. We will be using lighters. Okay, these lighters I got to fix still, but these lighters still light. We're not going to be lighting lighters. We're going to actually, do you guys know what's in here? Say it again? Butane. This is butane. Remember butane? C4H10? This is butane. Wasn't that on your test? Yeah. Yeah, butane. Butane. You guys kind of know butane is a fluid that can light on fire. It can combust. Well, I took the flints out, so there's no, like the little striker flints you guys like to strike just for fun? So that's what makes fire, right? It makes a spark. Well, there's a flint in here. When you do this, it flints and sparks and it lights the gas or the butane on fire. So I took those out. So when I do this back there in the lighters I have in the buckets, what comes out? What kind of gas? Butane. What's coming out now? More than that. No, butane plus oxygen's gone, guys. What did it make? Carbon dioxide and H2O and then some flame, right? So I can do this all day long, but it's reacting. So when I do this in the back with no flint, there is no reaction. What's coming out of the hole? Just pure butane. Now butane is a gas, right? It's a very pressurized. That's what the liquid in here. It's very pressurized. It's squished together, which is why it's a liquid. So what we're doing is when we click it and the butane comes out, we're relieving pressure and they just kind of float away as their butane gaseous molecules. We're going to capture those. We're going to capture them and then measure their volume. The way we're going to capture them is like this. We're going to have a little pneumonic trough or trough. It's just a bucket of water. Okay, we're going to put our hand underneath the water. There's my hand. There's my arm. Put our goggles on. Okay. Well, she knows both. Okay. So the butane lighter is going to go underneath the water, and we're going to click it. Click. And then we're going to let the bubbles come out. Well, if the bubbles just start coming out, we're just going to gas my room, and then the second I strike something, it's going to go up in flame. Right? Not a good day, especially the day we come back from spring break. We got to keep it under control. So we're going to keep it under control by putting it upside down. What am I drawing? Upside down graduated cylinder underneath. And then what are we going to do with the bubbles? Capture them. Okay, so we're going to capture our bubbles, right? Okay, so that's going to allow us to actually take the volume of the particular gas we're collecting. Now, can you see the gas? No. No, okay, I'm drawing bubbles, of course, but we can't see it. So what we have done previously is pre-filled the graduated cylinder with water. So as the gas bubbles, so it's filled with water all the way to the brim. As the bubbles come in, what has to go out? The water. So that's water displacement, correct? So you saw the water level. As the bubbles go in, the water comes out. The water can just kind of, go into the extra water that's there. We're going to stop collecting this once the water level and the gaseous level has met, meaning I can actually tell the volume of the particular gas at hand, and the pressure differences are not really a problem. So that's kind of the general process. Now, why am I doing this? I'm doing this because this butane lighter has butane in it, right? Has a gas in it. And I want you to prove the molar mass of the gas. Why do you think I just did number 8 or 19? So you know how to find molar mass of your gas. What was in problem 19 that allowed you to do that? Well, we found, what did we calculate in number 19? We calculated moles, right? We could easily do that because we had all these different variables. Pressure, temperature, and volume. Where do you think you're going to be getting those? From the lab. Volume, pressure, and then temperature. I'll give you a thermometer for it. So how do we get to molar mass? By moles, right? So that's how we get to molar mass. Where do you think I'm going to have you get your grams from? Say again? How do we normally get grams? We mass things. Okay, so how am I going to figure out the grams of this? Well, weigh what? You can't weigh bubbles, though. See, it's the problem. What made the bubbles? The lighter, okay? Well, Weigh it before and after. You see what I'm saying? That's the difference. The bubbles came out. What's the difference? It's the lighter, what it was previously, and then after, or taking the extra gas out. So let me show you this quick little idea of how to set this up. Get out a piece of paper. Let's call it Butane Lab. We have about 40 minutes. I think we can do this. We might be pushing it. All right, so basically the only piece of information that you would not have in the lab itself, like in the lab notebook, is right here, where it says write down. You absolutely will collect all of your data in class, and then if we have to finish up calculations, I get it during intervention time. I'd really like to focus on requests during intervention time. That's why I'm making sure you understand the timeline for today. So when we get back there, you'll get your goggles. You'll tie back your hair. Make sure that you have a 100 milliliter graduated cylinder in your little cubbies. If you don't, I'll make sure you get one. The pneumonic troughs are just big plastic buckets. I'll be handing those out to you. The graduated cylinder has those plastic pieces on it, like the base and then the little intermediate guy who's actually there to prevent falls and cracking in the graduated cylinder. You got to take the plastic off, but you got to make sure you put it back on because I won't know where it goes because it's really hard to see the water levels if you don't have all your plastic off. So the last part right here, it says dispose of butane appropriately. Butane is flammable, right? We don't want to just release it into the wild and go do your thing. No, we want to put this in a fume hood. So at the end of the lab, I will have you take your graduate cylinder like this with your hand on the bottom, keeping it captured, and then go to the fume hood and release it into the wild. Then we'll turn the fan on and be fine. Okay? Now this information here, you don't have in your lab. This is as of weather.com this morning, 29 inches of mercury, good old America. That's what our atmospheric pressure is right now. Now, I've given you this other conversion factor. What do you think you're going to be doing? Converting to what? Maybe millimeters. Why millimeters of mercury? Because it's a unit of chemistry that we can convert with, right? We can't do anything with inches of mercury. Heck no. So the other part is in our, I didn't show this earlier, but you know the water that was in the graduated cylinder? Well, it's just liquid. Well, can't liquids vaporize? Yeah, sure they can, right? So whenever you have your graduated cylinder, this is my little bowl, and I've got my gas in here, well, there's little just droplets of water still hanging out in there. So if I have my graduated cylinder and I have my pressure total, what two gases are inside that create that pressure? Butane and well, no, it probably is there, but I can't really calculate that. I don't have that kind of power right now. But I know I can figure out the butane pressure and I can figure out the water vapor pressure. And this is all at a particular temperature, and that temperature is the one that you collected in the lab. So there's like this book, it's about this big, and it has every single constant known to man, including every vapor pressure of water at every different temperature possible. We don't got that kind of time. So I pulled up a water vapor pressure chart, and that chart looks like this. And it will delineate, if you're at 2 degrees Celsius, here's your water vapor pressure, 5.3 millimeters of mercury. If you're at 7 or 8, you can see that it changes every time. So I'll leave that there for you as we go. I'll go back here for now, though. Other than that, I was going to show you this quick video of how she sets up, but I think you guys can read the lab. Yeah, you can do it. Oh, the only thing I'll say is right here. Hold on. All right, so here's this graduated cylinder you're filling up with water. There can be no bubbles in your graduated cylinder at all, because those bubbles would be problems with, meaning error in calculation later on. No bubbles at all, meaning it's going to be filled to the very, very brim. That means you probably do it over the sink because it's going to be spilling out. And then you'll take your graduated cylinder that's filled to the brim. You'll cap it with your hand, like really palm it, and then flip it over in your bucket of water so there's no bubbles. I'll help you get there. Okay. So you guys I have 8 groups. Go ahead, disperse yourselves into the lab stations. You guys can choose your own groups for now. You got about two minutes to get started. Okay, guys, let's go. Goggles on.
Alright guys, and lighters are coming. Coffee lab or butane lab? Alright guys, so listen up. I'm giving you about a minute to get your butts settled. And if we don't finish this now, do not use the lighters until I tell you to. I put them on your desk because I thought you were responsible. But molar mass of butane lab is going to be kind of like a one sheet in your lab notebook. You already have one on your desk. What materials method that you need to find? 100 mil graduate cylinder. Somebody needs to get going. The leader can get the group going. I don't care who the leader is, but you need to start practicing. You need to start getting your water. You need to let 2 minutes to get set up. That's it. You don't get set up. I'll be like, Okay, so those of you with the long little, what is it called? This thing, bucket. Okay, so those of you with the long one, you can do this one very easily. When I'm having you fill this water piece, there can be no bubbles up here, right? So if you just dunk it in here and you kind of get all the little bubbles out, you kind of shake a little bit, get the bubbles out, and then you just invert it or put it up. Look, no bubbles, right? And so what's going to happen is after Ivory and the group kind of gets finished with the math thinking from it, they're going to take their lighter and they're going to stick it right underneath the neck of the test tube, I mean the graduate cylinder, and they're going to light it with their hand underwater. Because if not, the bubbles won't get captured and there will be no water displacement. Note to yourself, if your water level isn't at least at the 100 mark, you're not going to be successful because you basically cannot collect gas below the 100. Why would that be?
Because
It's not what?
full.
Well, no, you can't collect gas and go, and then go down here and go, yeah, that's about 120 million. Because you can't estimate. You have to make sure it's correct. So don't collect gas below the 100. So that means your water level needs to be pretty high. If not, you're going to have trouble getting it to the point where you need to. I'll help you guys as you go. Keep going.
No, tell them to look sign.
I move this, I guess. I don't know what to do. Oh god. Oh gosh, I don't know what's going on.
Alright, so listen up. Those of you getting close to your final volume, once you're there, you're just gonna hold it awkwardly like Will, right? Well, William's got it now. He's captured it. He's going to release the water because water's not really helpful to release the water. And he's captured the gas. Okay, and he's going to walk to the new hood. And he's going to release the vial. Turning it up, turn up, and then we're going to stay there for about 30 seconds. If the gas is gonna do the same, we go back to it up. See, that's how you release the engine.
Which I probably got like a 1. You didn't look? No, I told you that. Oh. I don't. Wait, why? Huh? Wow, smart. Smart. Ooh.
Alright, if someone's not started taking inches of mercury to a more useful unit, you need to get on that. Partial pressure, pressure needs to be measured.
Oh yeah, we need to work on. Okay. Thanks. She's actually.
Alright, raise your hand if you need help, but otherwise I think you guys got it. You got 15 minutes. Knock it out.
So 20.
What are you looking for? 23. 21. Yeah.
So, guys, here's a heads up. If you just tell me butane's formula C4H10 and you do the more math that way, it's useless because I know you know that you're all smart people. My goal is for you to use data to find your answer, which is why you're in the lab collecting data, right? Use your data. Your data supports your work. Thanks.
All right, butts up here in 10 seconds, please. Laptops up now.
Thank you guys. Put your laptops up now. No. I got like 2 minutes with you.
All right, so hold your labs. I'll take them during intervention time. I know a couple of you guys did not get to finish the simulation before break, that gas simulation which was on PET. Some of you guys did, it was like 2 of you, 3 of you. So my goal is for you to finish up a couple things, wrapping up gases, because we're almost done with gases. We have the gas we can do tomorrow in Graham's law. So not too much more. So check out the board now. I'll leave it here on intervention time as well. Peace, get out of here, bring your lab back, we'll finish it up. I'll put it back up here. It's a very, number 9 has very body. Okay. Bye guys. I'll see you guys in like an hour and a half.
That's pretty cool, huh? No, it's good. Look. That gallon is long.
Okay, third period was a lot better.
Yes, I heard that too.
Like when we did our monster dance, I jumped over the
Okay,
car.
yes, I
People
saw
started
videos. You were
screaming.
awesome.
They started screaming. I was
Yeah,
like, this is what it feels like.
I saw like so many videos on Instagram. I don't know. Yeah, I was there.
Did you get
What is it?
national art?
No. 4.7. How did I not get that?
Maybe your first year.
Oh, I was in the trailer today. But yeah.
On the first day, and it's a red. It's like Carson.
After school? Directly after school?
Before even before school.
Can you start this? Did you start me? I need to go.
Look at this shit on.
Savannah, what number do you have? 17?
The numbers are off on the thing.
On the document?
For the project, yeah, the numbers are on.
Because I lost I tweeted my picture and I lost
It did hurt. I
Isn't
thought
it
it
recently
was
deleted? Isn't it recently deleted?
I don't know why.
Yeah, let me know what you have because I thought I had 18, which was the KB in Boston. And I don't have like, what are you doing? We done yet?
Number 18 on
Lucas, what do you have for this one? 17? The solubility product? 4.2.
Does anybody have a pencil like mine?
I have a pen.
That way
Hey guys, we're gonna start our practice exam. This is not. Oh, hold on. Still videoing. Honors Chem. It's for.